All right, so we're going to just kind of go into probability a little bit deeper. So Unit 4 is mostly a review of theoretically some probability tools that you learned probably in geometry, and then maybe even earlier in 7th and 8th grade. I get it that's for some of you guys that's been a really long time ago. Like, we'll talk about it some more, okay? So the first thing is doing a few more definitions. So the first one we're going to use is mutually exclusive. Have you guys ever heard of the phrase mutually exclusive before? Is that familiar to you guys? Do we remember what it means? For those of you shaking your head, yes or no? Okay. Two events are mutually exclusive if they cannot occur at the same time. Okay. So if I use like a traditional probability example, you guys, if I asked you to draw a card and I said, what is the probability that card is red and a spade? You guys with me? Is that possible? What's the one thing we know about the spades? They're the black cards, yeah? So, can a card be both red and a spade? No, so the probability of both of those things occurring is 0. Okay, so the biggest thing, if I were to look at that from a broader perspective, let's say we're talking about randomly selecting a person from this room. What is the probability that person is over the age of 40 and has straight hair? 0. And so for this group, that would be mutually exclusive. If we extended it down the hallway, maybe not. Because there's a couple other people over 40 who have straight hair. Everybody good? All right. So the addition rule basically says that if I want to find the probability of one event or another event, I'm going to find the probability of each of them and subtract the probability of both of those things occurring. So let's go through an example to explain why we do that. It'll make a little bit more sense when we do this example, okay? So as I'm looking at this, suppose 200 college students are enrolled in a nursing program, 150 in business, okay? Of the nursing students, 155 went to a program like the Career Center. Of the business, 64. What is the probability the student went to either the career program or majors in nursing? So this is an example of, like, on your test, typically what I'm going to do is I'm going to say build the two-way table. Okay? So what are my variables? Like, as I select a person, what are the things I'm going to ask that person in order to find the information presented to us? So the first one is like which major. So, all right, so one of my variables, so I'm going to put that one across the top, is the person a nursing student or a business student? And like we talked about the other day, I might call this one N and this one B. Just representing them with capital letters, okay? So one variable with the possible responses goes on one part of your table. The other one's going to go up and down this vertical axis here of my table. What is the other one? Career or not. And what I might do here in this particular one is I might use C. And for this one, I might use C complement for 2 reasons. Number 1, I already have an N. And 2, like, this is the opposite of this. All right. And then when I build a two-way table, because one of the things I find useful about them, I like to add one more row and column for the totals. So the first thing that in the past where students have struggled is they might try to put nursing here and business here, right? So these two have to be two different responses to the same question. And you could have 2, 3, 4 responses if you want. You can have multiple columns here, okay? And then these are, so like the reason I kind of focused on what question are we asking is because these are all responses to the same thing, okay? All right. All right, so now let's fill in the numbers based on what we know. Do we know any of these? Help me fill in this table of what we know. Okay, so where would the 200 go? Is that describing the nursing students at the Career Center, the not Career Center, or the total? The total. The next thing, 150 students, business students, that's describing the total. So already I can fill in one more box. What do I know about, if I know these two, I also know that this one would be 350. What else do I know? So where does that go? Top left. I would call that they are both nursing students and, so this would be, like for any one of these, we would use the word and to be able to describe where that person is. Is everybody good? Let's see. And then I know 164. It's in the wrong box. At this point, do we have enough information to fill in the rest of the table? So go ahead, fill in the rest of the table. Let's make sure we're all on the same page of where. Guys, if you don't have your calculators out, take them out. We're gonna be using them all day. What are we getting right here?
219.
And let's go, just read across.
45, 86, and 131.
Are we feeling good on this? Okay. So, one of the very first questions on your test is going to be, I'll give you information like this one and ask you to create a two-way table, okay? All right, from there, I'm gonna ask you to find some different probabilities based off of that two-way table. So this original question is asking us, what is the probability that a student went to the Career Center or majors in nursing? All right. So what if I asked you just, what is the probability someone went to the Career Center? What would we want to look at?
Total careers.
The total of the Career Center over the table total. Okay, great. So 219 out of 350, yeah. All right. Addition rule says they add. What is the probability somebody is a nursing student? $200 out of $350. You guys, if I add those together right now, I get 419 out of 350. Is that a possible probability?
Yeah.
What is 419 out of 350? 1.197?
They can't be above 1.
Probabilities can't be bigger than 1. So let's look at what happened, okay? So that 219 out of 350 was adding together this row. That 219 was that row, yes? And the 200 was this column. Do we see that the 155 was counted twice?
Yeah.
Is everybody good? Okay, so what we need to do is subtract away the probability of C and N. Because when I do just the probability of C, I've counted the people who are C and N. And when I do the probability of N, I've counted that. So like this takes, by taking away this once, everybody in this box counted twice. Okay, now, the minute I do that, my probability will be smaller than 1. Is everybody good? What are we getting, y'all? 0. Great. Now, if you want to attack this question differently and be like, okay, I'm only going to look at these numbers because these are the ones that represent actual people. These ones are kind of summaries of the rest of the table, okay? I could go in and say which ones are either nursing and or business and just say that's this box plus this box plus this box. And if you add the boxes instead of the totals, that'll take care of that too. Okay, now, so do we see now why the probability of A or B is not just the A and the B added together? You have to subtract away that overlap. Okay, this formula is on your blue sheet. So that's not one of the ones where, that's not one you need to study, as long as you're good at saying, you're having this out there and saying, hey, I don't know how to do this problem. Is there something here that will help me? Do you guys get what I'm saying here? Okay. All right, so that's the addition rule. All right, so let's say I am randomly selecting a card from a deck. What is the probability of drawing a card that is either an ace or a king? So if you're somebody that likes to have like the set of rules to follow, okay? This is when, before I did anything else, I would actually write down the rule that that would be the probability of A plus the probability of K minus the probability of A and K. I would say, hey, I like a rule to follow. I'm going to go to my formula sheet and see what the rule is and go from there. So, you guys, do we know the probability of a card being an ace?
4.
There's 4 aces there's 52 cards in a deck. You guys, it is not an expectation of this course that you know decks of cards well. All right, we're going to use them as examples. I will happily explain what's in a deck of cards. If you didn't grow up playing cards, you wouldn't know a deck of cards well. I get that, okay? The questions on your test won't rely on that. You'll have enough information to answer the questions from the information in the test. Is everybody okay? All right. What's the probability of a king? 4 out of 52. What is the probability of a card being both an ace and a king? 0. Okay, so overall probability is 8 out of 52, which is 8% maybe? I can't have it that low.
.153.
Okay, you guys, what can we say, knowing this, what can we say about aces and king, a card being an ace or a king? They are, what word? What words did we learn like 2 seconds ago? They are mutually exclusive. One occurring excludes that the other one can occur. Is everybody good? All right. What is the probability that a card is an ace or a heart? Again, I don't need to see this written out, but it is a way of like, this is how you can be thinking it through. Okay. Now, we just said the probability of an ace is 4 out of 52. Does anybody know the probability of a heart?
13 out of 52.
13 out of 52. Are there any cards that are both ace and heart? How many? 1, the ace of hearts. I'm assuming 306 should be double. All right, let's do one more example of these. So we have a couple of thoughts here. So my first instinct, if I were to do this question or make up my answer key, would not be to try to just use the formula. I would build the two-way table because it makes more sense to me to do that. So if I'm building a two-way, plus I think it's good practice. If I'm building the two-way table, what should go across the top versus, what are my variables?
Cyclists, runners, male and female.
So one variable is the activity. Cycling versus running. Okay? And then okay. Let's start filling in some numbers. Tell me anything.
13, 7, 20.
The first column is 13, 7, 20. And then
18.
12, 30. And then you guys count across, yeah? Okay, and then the question is saying, what is the probability of cyclist or female? So I'd probably look at this as like, I could do these three numbers on, those are the three boxes that are cyclist or female, right? So I could look at that and do 13 plus 18 plus 7 over 50. If I'm following that formula, I could do the cyclists, the females, minus cyclist and female. No. You guys, I did this one. Remember when I said cyclists and females? I circled the wrong one. There we go. All right, so if I do this top one, we should end up with, that looks to me like it adds to 32 over 50. If I do this one, I should get 32 over 50. So notice that we're getting, whether you take, it doesn't matter to me whatsoever what approach you take, okay? I'd even listen to, well, isn't that everybody but this group? And do 1 minus 18 over 50. Whatever approach you take is absolutely fine with me. It's got to make the most sense. I just don't want you to make the mistake of doing this number plus this number without subtracting the overlap, recognizing that overlap exists, okay? Okay. All right, there is, for this multiplication rule at the bottom here, guys, there's definitely, I know what happened. It turns out that in order to type 60%, you have to hit, to get that percent, you have to hit shift 5. And I obviously didn't hit the shift. So that's 60%, that's supposed to say 60%, not 605. Okay. Okay. All right, so the multiplication rule is when we have more than one event occurring, okay? So whenever we have like this event, then this event, then this event, then this event, what we do is multiply probabilities. Okay, so so if I have, what is the probability? So for each individual person, they're all smokers. They're going to go through hypnosis to try to quit smoking. Okay, all right, and so the probability of success for any one person is 60%. Okay, so what we're going to do is we're going to take the probability the first person quit smoking, and so first person quits, second person quits. Are you guys with me? Those are two separate events. There's the uncertainty about the first one quitting, then the one by the second one, and then the third, okay? So this is like saying the first one quits, and the second one quits, and the third one quits, and the fourth one quits, and the fifth one quits. Are we starting to get a feel? And whenever that's the case, what we do is we multiply the two events. Okay? So what is the probability the first person quits? 60%. Then I'm going to multiply by the probability the second person quits. The probability the second person quits is? It's also 60%. Third? 60%. How many of these are we going to have? 8. So how else could I write this? 0.6 to the 8th power. And I would imagine it's a really small probability. 0.016. 0.016. I was going to say 0.16 would be pretty likely still, I think. Okay. You guys, what is the probability that no one quits?
Would it be 0.4 to the 8th power?
Yeah. You would say, well, what's the probability of the first person? It doesn't work for the first one, times what the probability doesn't work for the second one, times etc. Okay? So it's really, really small. In fact, it might even be in scientific notation. Does it give it to you? What does it give you?
6.5536 times 10 to the negative 4th.
So I'm going to call it 6.55 times 10 to the negative 4th. You guys, that times 10 to the negative 4th is telling us it's really small, right? It's telling us to move our decimal place, yeah?
Do you want us to keep it in scientific notation?
I don't think I care. I can't promise that on the online homework that they don't have, like if they say to 4 decimal places, they're going to want you to write it as a decimal. Do we need review on how to write scientific notation as a decimal? You just move it over that many times. So you always end up with one less zero than the exponent is, right? Because you always move it over the first one, and then whatever that exponent is, you'll have that many less zeros or whatever, okay? All right, one more question. What's the probability at least one person quits? It's not, because, so we are going to learn this the long way, okay? In fact, we're going to do that on Thursday probably, okay? Are you with me that at least one is everything but none, right? Like, of these people, you could have 0 quit, 1 quit, 2 quit, 3 quit, 4 quit, 5 quit, 6 quit, 7 quit, 8 quit. Those are all my possibilities of this happening. So at least one is everything but none. So I can just do 1 minus the probability of none, which we just found. Also a formula on here. The probability of at least one is equal to 1 minus the probability of none. All right. We're going to get through these ones and then we'll take a break. Okay. Marbles selected from a bag containing 4 red, 5 green, 6 blue. So, how many total marbles do we have here? 15. All right. We're going to replace the marble after each pick. What is the probability that I get 3 green marbles in a row? Everybody good? So, essentially what we're going to do is the probability that the first is green times the probability that the second is green times the probability that the third is green. What is the probability that the first one's green? 5 out of 15. Times, what's the probability the second one's green? Okay, so in this case, we're putting the marble back, yes? So once I put that marble back and I mix them all up again, I'm still drawing out of 15, and there's still 5 that are green, so it stays 5 out of 15. For each one of these. Which works out to be 1 out of 27 when you multiply it across, because it's 1/3 times 1/3 times 1/3. Which is probably just short of 4%. Was that close?
It's 0.037.
37. How would that change if after I pull a marble out, I didn't put it back? Okay, so let's think, we're still gonna do the first marble times the second marble times the third marble. Okay, what's the probability the first marble is green? 5 out of 15. Now, if I don't put that marble back, how many green ones do I got? 4. How many, and then how many am I drawing from?
14.
And then that third marble would be 3 out of 13. Okay. So, this top is an example of what we call independent events. And the bottom is what we call dependent events. Okay. So, for the top, because we were replacing that marble each time, this probability was, the probability of green stayed the same the whole time, okay? So the idea of independent events essentially means two events are independent when one event occurring doesn't change the likelihood of the other occurring. Okay. So, whatever happened on that first draw, because I put that back, that next draw, the probability stays the same. Okay? Whereas on this one, let's say I hadn't drawn a green on the first one, all of a sudden this probability is either going to be 4 out of 14 or 5 out of 14 depending on what happens here. Does this make sense? Are we good? Okay, so we needed to know what happened here in order to make sense of this, to make this happen. And even no matter what, knowing that this one was green changes whether or not this one is the likelihood of this one to be green. Is this okay? All right. So dependent events, one event occurring changes the likelihood of the other occurring. All right, we're going to take a break. We're going to come back in about, say, 5 minutes. Everybody's back by 8:45. I'll start the second half. And we'll do just some more questions related to this topic and talk about conditional probability. Maybe to kind of firm up some kind of tricky topics, I've got a side question. Can two events be independent and mutually exclusive?
Yes.
I think.
Yes?
I think
No?
Yes.
yes.
Yes? Yes? So we only one no? Liv's the only no?
I'll change my answer. Yeah, me too.
Liv, what color you want?
Red, please.
You did that on purpose, didn't you?
Thank you.
Okay, me.
I'm not really good at catching.
I'm not really good at throwing.
No, you can catch that.
I'm not really good at throwing. We'll just do that.
Thank you.
You only get it if you catch it.
Okay. All right.
I'm just
So,
doing something.
you guys, if I know, first of all, right now, we have a probability of somebody in this room having curly hair. Everybody with me? I'm sorry, straight hair. Straight hair. We could figure that out, yes? Okay. All right, hold on. What if I know that the person is over 40? Does that change the probability of them having straight hair? Is everybody with me? In this room. Is everybody with me? Now, we said earlier being over 40 and in this room is, or being over 40 in this, like if this is our group that we're drawing from, being over 40 and having straight hair is mutually exclusive, right? So, the minute I know that somebody is over the age of 40, the probability of them having straight hair goes down to 0, yeah? If two events are mutually exclusive, knowing one of them occurs tells me the other one hasn't.
So then it doesn't affect.
The definition of independence is one event occurring doesn't change, but if the two events are mutually exclusive, the one occurring tells me the other one isn't. Are you with me? So two events cannot be both independent and mutually exclusive because I know for sure that the second event can't occur if the first one has. Does that make sense now? Okay. All right. Now, that is not something you're going to be asked on a test or anything like that, but the big conceptual understanding of these two things is kind of why we think through this question, okay? All right. You draw 3 cards from a standard deck without replacement. What's the probability of all 3 cards being a heart? Talk me through it.
13 hearts in the deck.
Okay. So, there are, in fact, at the beginning of a standard deck, 13 hearts out of 52 total, yes? So, the first card is a heart. The probability is 13 out of 52. What's going to happen on that second card? If I don't replace that first one, it now has a probability of 12 out of 51. So the probability the third one's a heart?
11 out of 50.
11 out of 50. What are we getting?
0.013.
Are we all good? All right. As the chair of a committee, you must select 5 people from your department of 13 men, 16 women. What is the probability that you select all women? So, take this through. What does that mean? First person's a woman, second person's a woman, third person's a woman, fourth person's a woman, fifth person's a woman, yeah? So, I start with 13 out of 29 times.
13 out
If I'm selecting for a committee, am I replacing or not replacing? I'm not replacing. Are we all good on that? Because, like, if I'm selecting 5 of you to be in a committee, if I put you back, I might end up with the same person on the committee twice, which doesn't make sense. Okay? So probably the next person's a woman? And why am I taking this out so far? Yeah, I have 5 fractions for the 5 selections. Oh, definitely should have charged this while you guys were on break. What are we getting, y'all? 11 over what?
0.011.
Hold on, that's okay. What did you get? 11 out of 1,050? Is that what you said?
No, 15. 1,050.
And does that work out to be what?
0.011.
Yeah, that's right.
It's fine. Okay, we're all on the same page. Hey guys, so the next question is, what is the probability of at least one male? Okay. We just said the other day in this, or a few minutes ago, and it's on that blue formula sheet like this. It says the probability of at least one is equal to 1 minus the probability of none. Are we comfortable saying the probability of all women is equivalent to the probability of none male? None men? Is that making sense to think of it that way? So if I say, so the probability that we don't have any guys on this committee is 1.1%. What is the probability that we have at least one? We do. 1 minus that probability. So the probability of at least one male would be 1 minus the probability of no males, which is 1 minus the probability of all females. I can't you guys, I can't emphasize enough, and it's on your formula sheet, but I can't emphasize this kind of reasoning enough, because it's the precursor to some reasoning that later on is something that you might struggle with. So if we're struggling with that idea, I can come up with some more visualizations of why that occurs. Okay? That's a really important idea that we need to understand. Are we good? Yes, no. Okay. All right, great. I think I want to test how are you guys actually doing with this? I want you guys to try this one on your own, please. I believe in you. I wouldn't have you try this on your own if I didn't. Do you guys see what I'm saying? And so if you're one of those people that likes to have the same set of rules and the same process that you follow every single time, you can always use the formula, but I think there's value in both. In understanding that they both get you to the same place, whatever makes the most sense for you is actually the most efficient. Is everybody good? Okay, let's look at this. So I'm going to call this accident. We're going to say someone was in a car accident versus not in a car accident, and then cell phone, not being on the cell phone. In this particular case, I think it makes a little bit more sense to use that language, given how these are very, very black and white, yes, no questions. Okay? But if you did it's just that one, if you use different symbols, it's fine. As long as I can understand what they are, you're good. Okay? All right. So the question becomes, find the probability of getting into a car accident given that you are using a cell phone. So, you've got a two-way table here, right? Though this two-way table is a little bit different than the previous one because what's not here that was there before? The totals. Can we add the totals pretty quickly? Yeah, you guys, 3 plus 18 is, I'm going to add them in a different color, is 21, 10, we got 4, and 27, and those all add to 31. And that's working out quite nicely. Okay, so given the two-way table, what do you guys see? What do you guys want to do here to come up with this answer? So we want to know, given that somebody's on a cell phone, what's the probability they get into an accident? So are we all comfortable with 3 out of 21? It's the minute I have that given, I'm hyper-focusing on this column. Is this okay? 3 out of 21 is, 1 out of 7 is 14.3%. Sure wouldn't mind if somebody checked that on me. You guys, what about the other way around? What is the probability you get into an accident given that you weren't on a cell phone? 1 out of 10. I don't need help with that one. Is that a big difference? 14% versus 10%?
Yeah.
I think that's a pretty big difference. It's almost 1.5 times it. What, like, I think that's a pretty big difference. Yeah. Okay. All right, so if I gave you this table, could you tell me which is more likely to run a marathon, males or females? Are female runners or male runners more likely? So the probabilities we would want to find there is, well, what is the probability of, I'm going to call this R for running since we have male and female. Is that okay? Okay. What's the probability of running given that you're a male? What's the probability of running given that you're a female? So no matter what, if I'm given this two-way table before I do anything, before I even think about the question, really, I'm doing this. I can't think through this without having those totals there. Are we all comfortable with that idea? So, which group's more likely? Females are slightly more likely to run a marathon than males. Are we good? Okay. Just gonna do this and I feel like I didn't hit record again, so I wanna just let people copy these for a second. So I'm gonna just leave those with the recording running for the people watching the recording at home to copy what I. Okay, well, while that's happening, pass those out to you.